Hi everyone, in this video we'll be looking at empirical and molecular formula. Let me draw your attention to this table. The column on the left shows the molecular formula, while the column on the right shows the empirical formula. Do you notice how they are related? I think it'll be quite obvious to you that when we simplify the molecular formula to the simplest ratio, we get the empirical formula. For example, P4O10, the ratio of phosphorus to oxygen is 4:10, which can be simplified to 2:5. You will also notice that for some molecules, the empirical and molecular formula are actually the same because the elements are already in the simplest ratio in the compound. So in cases where the empirical and molecular formula are not the same, the molecular formula is always a multiple of that of the empirical formula. And this is usually a whole number multiple. So for example, in C4H10, right, this is 2 times that of C2H5 lah. So you may wonder, right, where does this concept of empirical formula come about? The word empirical suggests that it is experimentally determined. So in the early days, right, okay, let's say we know that this compound contains 2 elements, okay, but we do not know the ratio in which they combine together. So let's take this Lego for example. This Lego can be seen as being made out of 2 elements, right? One blue, one yellow, the top and bottom. And I do not know what ratio they are combined in. So we'll carry out what we call elemental analysis. Let me break this apart. Okay, I'll weigh this. And if I know the individual mass of one block, I will know how many blocks I have. Okay, I also weigh this. If I know the individual blocks of one of these, I'll know how many of these I have. Then I'll find the ratio in which they are present in this compound. So for example, in this case, this is 2:3. Yeah. So by finding the mass of each element and you know the individual unit, right, mass unit of each element, you can find the ratio in which they combine together to form a compound. Okay, so this is a very simplified way of explaining the concept of empirical formula. The empirical formula of ethane is CH3. Given that the relative molecular mass is 30, what is the molecular formula? So we know that the molecular formula is always a multiple of the empirical formula, right? So we can write it as CH3 bracket n, where n is a whole number. And we can calculate in this formula that there will be n times of C and 3n times of H. AR of carbon is 12 and AR of hydrogen is 1. This is 30. You find that n equals 2. So therefore the formula is C2H6. Of course, there's more than one way to do this. You can also calculate the relative molecular mass of the empirical formula where you get 12 plus 3 equals to 15, right? And you find that 30 is actually 2 times of 15, and you can also conclude that n equals 2. So you don't need to use any algebra at all. So how empirical formula is determined is through experiments. Okay, so this is one example of how the empirical formula of magnesium oxide can be determined. Of course, we already know, the formula of magnesium oxide, that is MgO, right? Okay, let's say this is an example we are not familiar with. This can be done using the same method now. So we'll start, let's say I start with magnesium, 1.20 grams of magnesium. Where I heat it, it reacts with oxygen to form magnesium oxide. Okay, so I can weigh. Before, magnesium is this mass. After reacting with oxygen, this is the final mass. I know the difference in mass is due to oxygen being gained, correct? So I can work out that the mass of oxygen that combined with magnesium is 0.8. I can subtract the initial mass from the final mass. So we will always start with a mass ratio. So this is 1.20, this is 0.8. Of course, we cannot use the mass ratio as the ratio of atoms, right? So we will need to find the mole ratio because mole is the unit of counting, the number of particles. Okay, so the relative molecular mass which we get from the periodic table is like this. Then we always start by finding number of moles, which is the mass over the molar mass. So I'll take 1.20 divided by 24, 0.05, 0.8 divided by 16 equals to 0.05 moles. So the mole ratio is 1:1. Therefore, the formula of magnesium oxide is MgO. So this is how it's usually done. We can draw a table, put the elements in the columns, then we have mass, put the AR, find number of moles, and then mole ratio. Okay, so you can draw this table in exams as well, and I summarized the steps in this box above. So let's try a few examples together. And with each example, there is a key message that I want to let you know. Similarly, we're going to do this question where we have an element that reacts with oxygen to form an oxide, and we want to find the empirical formula of the oxide. So I start off with 0.02 mole of an element M reacting with 0.025 mole of oxygen gas. This time round, instead of mass, I give you in moles already. Okay, so we are actually finding the formula of the oxide of M, which is the ratio of M atoms to O atoms. The number of moles of M atoms is 0.02. Okay, it says that it reacts with oxygen gas. Remember, oxygen is O2. So if I have 0.025 mole of O2, I will have 0.05 mole of O, because every molecule has 2 atoms. So oxygen is diatomic. So if I have 1 molecule of this, I will actually have 2 atoms of oxygen. So if I have 1 mole of oxygen molecules, I will have 2 moles of oxygen atoms. So when we compare empirical formula, we always use the ratio of atoms in a formula. Okay, we don't compare molecules. So the mole ratio here is 2:5. So the empirical formula is M2O5. What do we need to find out what's the molecular formula? We will need the relative molecular mass or the molar mass of the compound. Okay, so the key message here is, if you are talking about oxygen gas, a common mistake is for students to put O2 here, which is wrong. Always compare the ratio of atoms in the formula. Let's do the second example. If you are confident, you can pause the video and give it a try first. Okay, then I'll go through with you. So likewise, we draw a table and we have the individual steps, always starting with mass. The mass of iron is 0.3450. My initial mass was this. I'm removing the oxygen away. So the difference in mass is the mass of oxygen, which I subtracted, 1314. Check the periodic table for these values. So we find number of moles, mass over molar mass, you have 0.00616 here and 0.0082125. If I ask you what is the ratio of these two numbers, it's a bit difficult to figure out like this because it's not whole number like the first example 2:5. What you can do is to divide by the smallest number. And what does it mean is you compare all the numbers. In this case, 0.00616 is the smallest number. You divide it by it, you get 1:1.33. Okay, and that will make it a little bit easier for you to figure out what are the ratios, which you can work out to 3:4. Okay, 1.33 being 4/3 lah. So the empirical formula of the oxide will be Fe3O4. Okay, so that's the key takeaway from this question is if the ratios are not exact, you can find the mole ratio by dividing throughout by the smallest number. Okay, let's look at one more example. I'll encourage you to give it a try first, okay, before I go through the answer with you. Question 3, I'm given the molar mass. Okay, so this will be important information later on. This gram mole minus 1 is actually the same as gram per mole, just a different representation. This time round, we are not given moles, we are not given mass, we are given percentages. The percentages shown here are by mass. So meaning, if the percentage is 40%, in 100 grams, I will have 40 grams. Okay, so we convert the percentages to mass, then find number of moles. I think you can do this. Okay, so convert mass to mole, divide by the molar mass, 40/12. Okay, so here, I think you might be able to visually see that it is 1:2:1. Okay, but if you can't see that, it's okay. The trick is to divide by the smallest number. So 3.33 is the smaller number here. Divide it, I will get 1:2:1. That's the mole ratio. So the empirical formula, we can write it as CH2O. Since the molecular formula is the multiple of the empirical formula, you can let it be CH2O bracket N. Molar mass is already given in the question, right? 90.08. So the relative molecular mass, if I were to calculate this, will be 12 plus 2 plus 16. And it will be N times, right? So in other words, is 30 N. 90 and 30, this is a 3 times, N will be 3. So that means the molecular formula will be C3H6O3. So example 3, the key idea is if you are given percentages, just convert it to mass. Question 4 is actually quite a common question in O-levels, especially in the practical setting. These are masses you can weigh in the school lab, and it is a simple experiment you can carry out. So we have 27.8 grams of hydrated zinc sulfate crystals. Remember, in a hydrated salt, we write it in this format where we have the water of crystallization. Okay, so we heat the hydrated salt, we will get rid of the water of crystallization, and we'll get the anhydrous salt. So in this case, I have 16.1 gram. I start off with 28.7 gram. You can kind of work out what is the mass of water that is lost already. Okay, so maybe you should give it a try first, then I go through the answer with you again. So notice this time around, I'm not even giving you the headings. What are you going to write? Okay, give it a try, then I'll go through the answer. So in finding what is the formula, right, I'm interested to know what's the ratio of zinc sulfate to water. This time around, you see, I'm not putting the ratio of atoms in an element because I'm interested to find out the ratio of the anhydrous salt to the water of crystallization. So I'll put those as the column headings instead. Same thing, I'll start with the mass. So the number of moles here, instead of dividing by the AR of the element, I'll need to sum up 65 plus 32 plus 4 times 16. Number of moles is 0.1 mole. Do the same for water, 18, 0.7. So the mole ratio is 1:7, which means the value of X here would be 7. So the chemical formula is actually zinc sulfate dot 7H2O. Okay, so sometimes when we do question involving water of crystallization, we find the ratio of the ionic compound to water instead of the elements ratio, but the method is the same. Alright, so I hope that these 4 examples gives you a better idea on how to approach this type of questions. And that's all for this video. I'll see you in class.